Have you ever stopped to think about what's really going on inside your phone? I'm not talking about the chips or the wires, but the deep, fundamental rules that govern literally everything it does. Well, it turns out from the smallest smartwatch to the biggest supercomputers on the planet, they all play by the same set of rules. Today, we're going to go on a journey to understand those rules. We're going to climb the ladder of computational power, one rung at a time. So, here's our roadmap for the climb. We're going to start at the very bottom with the absolute basics. What information is even made of? Then, we'll meet our first and simplest little machine, the finite automaton. After that, we'll give it a memory upgrade to build something called a pushdown automaton, before we hit the top of the ladder with the legendary Turing Machine. And once we're up there, we're going to stare into the abyss and ask a really wild question. Even with the most powerful machine imaginable, are there some problems that computers can never solve?
Okay, so before we can start climbing, we need to make sure we're on solid ground. Before we can even talk about machines that do stuff, we have to agree on the stuff they're working with. And in computer science, that all starts with just a few simple, really foundational ideas.
It all builds from the ground up, and it's simpler than you might think. At the very bottom, you've got a symbol, like the letter A or the number 0. A collection of those is called an alphabet. Then you just string them together and you get, you guessed it, a string, like ABA. And the final piece of the puzzle, a language is just any collection of those strings. That's it. From these 4 ideas, we can frame basically any problem a computer could ever tackle.
Now, this is a really important point. When we say language here, we're not talking about English or Japanese. It's a very precise mathematical idea. A language could be the set of all valid credit card numbers, or the set of all DNA sequences that code for a specific protein. The whole game of computation is about this. Can a machine look at a string of data and decide, yes or no, does this string belong to the language we care about?
All right, with our basic terms locked in, we are ready to take our first step up that ladder. It's time to meet the simplest computing machine you can possibly imagine, the finite automaton.
You can think of a finite automaton, or FA for short, as a really simple gatekeeper. It looks at a string of symbols, one by one, and switches between a few preset states. Like a traffic light goes from green to yellow to red. When the string is done, the state it's in tells you the answer, accepted or rejected. But here's the kicker, and it is a huge one. It has absolutely zero memory of the past.
The vending machine is the perfect analogy. Let's say it needs 50 cents. You can put in 2 quarters or 5 dimes, it doesn't matter. Once it hits that 50-cent state, it has no idea how it got there. It only knows its current state. It has no scratch pad, no way to write down notes about what happened before. Let's watch one in action. Say we have a machine that's supposed to accept strings that start and end with the letter A. So if we feed it ABA, it starts in state Q0, it reads the first A and whoop, moves to state Q1. Then it reads the B and moves over to Q2. Finally, it reads that last A and moves back to Q1. The string's over, and because Q1 is one of our special accepting states, bingo, the string is accepted.
But that complete absence of memory is its Achilles heel. It means an FA is totally helpless when it comes to patterns that require any kind of counting. It could never, ever verify that a string has, say, 5 A's followed by 5 B's. Why not? Because by the time it gets to the very first B, it's already completely forgotten how many A's it saw. So that exact limitation, that inability to count, means we have to build something better. To solve more interesting problems, our machine needs some kind of memory. So let's climb up to that next rung on the ladder and give it one.
Here is the classic problem that just breaks our little FA. The language of some number of A's followed by the exact same number of B's. An FA is going to fail this test every single time because, like we said, it just can't count the A's to check against the B's. To solve this, we need an upgrade.
And here it is, the pushdown automaton, or PDA. It's basically our old FA, but we've given it a new superpower, a stack. Just picture a stack of plates. You can put a new plate on top, that's a push. Or you can take the top plate off, that's a pop. This simple little memory structure is a total game changer. Now, for our problem with the A's and B's, the solution is so elegant. For every A you see, you push a token onto the stack. Then, for every B you see, you pop one off. If you finish the string and the stack is empty, boom, you know the numbers matched. So here's the difference in a nutshell.
The FA, with no memory, can only handle simple patterns we call regular languages. But by adding that simple stack memory, the PDA can now handle more complex stuff, like nested parentheses or simple counting. This unlocks a much more powerful class of languages called context-free languages. We are definitely making our way up that ladder.
So we've gone from a machine with zero memory to one with a simple, last-in, first-out memory. But what if we just blew the doors off? What if we gave our machine unlimited memory? What could it do then? Well, this question brings us to the very top of our ladder, to the theoretical model that defines the absolute limit of what we even mean by computation. This right here is the Chomsky hierarchy. It's basically a map of computational power. Each level is nested inside the next, showing a bigger and more complex universe of problems. We started down in that tiny core with regular languages and our FAs. We climbed out one level to context-free languages with our PDAs. And now we're heading for the big one, the outermost layer, the domain of the most powerful machine ever conceived.
And this is it, the Turing Machine. The amazing thing is how simple it sounds. It's just a little control box, kind of like our FA, with a tape head that can read and write on a tape. But here's the key. That tape is infinitely long. It can read a symbol, write a new symbol, and move left or right on the tape. That's all it does. But that infinite tape, that unlimited memory, that's what gives it the power to compute literally anything.
And this is the part that should really blow your mind. The Church-Turing thesis basically says that anything that can be calculated by any methodological process, by any algorithm whatsoever, can be calculated by a Turing machine. I mean, think about that for a second. This simple, imaginary device is, in principle, just as powerful as your laptop, your phone, or the most advanced supercomputer we will ever build. It's the gold standard. You can really see the difference in power when you look at a table like this. Now, don't worry about what union or intersection mean right now. Just look at the pattern of check marks. See how the regular language column is all neat and tidy? They're simple and predictable. But as you move right into the more powerful languages, you see more of those red X's. Things get a little wilder. They're more powerful for sure, but they're also way less predictable. So we have our ultimate machine, the Turing machine, a machine that can compute anything that is computable. Which, of course, leads to the next, almost philosophical question. Are there problems that are just not computable at all? The answer, incredibly, is yes. And this is the line in the sand. A problem is called decidable if we can build a Turing machine that is absolutely guaranteed to stop and give us a clean yes or no answer, no matter what we feed it. But a problem is undecidable if no such machine can possibly exist. For some inputs, any machine we build to solve it might just run forever, stuck in a loop, never giving us an answer.
And listen, we're not just talking about a handful of weird niche problems. The number of undecidable problems is infinite. There are infinitely more questions that we can ask than we can ever build machines to answer. It's a fundamental limit to what logic and computation can do.
This table just says it all. Look at the world of regular languages on the left. All the big, important questions are decidable. Can we figure out if a string belongs to the language? Yep. Can we tell if two machines are doing the same job? Yep. But the moment you jump over to the power of a Turing machine, those exact same questions become undecidable. The price of ultimate computational power is a profound uncertainty.
And of all the undecidable problems, this first one is the most famous, the halting problem. It sounds so simple. Can you write one master program that can look at any other program in its input and tell you for sure whether that program will eventually stop or just run forever? And the amazing, proven answer is no. It is impossible. No such program can ever be written.
So we've climbed the whole ladder. We went from a simple gatekeeper all the way to an ultimate machine with infinite power, only to discover that even at the very peak, there are cliffs we can never, ever climb. This journey doesn't just tell us something about computers, it tells us something about the fundamental limits of knowledge itself. And that leaves us with a final, big question to think about. What does it mean to know that we live in a universe where some questions simply don't have a computable answer?